Hello guys, nice to see you.
Good afternoon.
Hi.
Hello.
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 Hi.
Hello.
Good afternoon.
Good afternoon.
Hello.
Hi,
Yeah.
nice to see you.
Hello.
Hi.
Hi.
How are you today, Mr. Viktor?
I'm fine, thank you. Was in gym in the morning, wake up and doing well. How are you?
All right, thank you.
Cool. Are you guys all from Kazakhstan or there are some foreign students?
Hello.
Hi. Yes, I know majority of students are from Kazakhstan. Okay, I believe that most of people who wanted, they join us. Those who will be interested to join can do so on the way. First of all, I would like to mention that you should already have access to Lonkapa. So encourage you to try to log in, check how it looks, how it works. You should also have assigned homework. So this is week number 2. As I mentioned earlier, this homework will not be graded, so it will not contribute to your final grade. Don't worry, you can practice and try things during this week, so you have a chance to learn how it works and how to submit answers in Lonkapa. Please be very careful with the format. So it is important that you submit according to the required requirements from the Lonkapa, because otherwise your solutions will not be accepted even if they are correct. So did someone already have a chance to try to log in? Did it work for you?
Yes,
Yeah.
it worked.
Yes.
Okay, so what, you used your NUID credentials?
Yes.
Mhm.
Yes.
Okay, cool, that's good. If in some case for someone it doesn't work, please be aware that you have this option to contact our Lonkapa administrator, and he will definitely help you. But I believe the majority should be totally fine with Lonkapa now. Okay, any questions on this moment with Lonkapa, with homework? Everything is clear now.
No question.
That's great. Good. So starting from 3rd week, you will already get homework assignment, which will be graded. So also keep in mind that. So we, during our last discussion, had introduction of vectors, like the concept of vector, first of all, why we need it and what it gives us. Also, how we can deal with vectors in terms of adding them, subtracting, we introduced the unit vector, which is very useful concept when we quantitatively work with vectors, so we can split them in different components along the respective axis. Also discussed two options to multiply vectors, like dot product and vector product of vectors. So pretty much all the necessary information which can be in this or that form mentioned during our course. So now we technically start with the main subject, with kinematics in this case. And the main task of kinematics, could someone please help me to define the main task what kinematics solves, and which question, the main question it answers?
Why the objects move?
No, that is important question, but not from kinematics point of view.
How fast objects move.
Okay, that is closer. So mentioning about this first comment, why objects move, that is dynamics. That is our second chapter of mechanics, which we will discuss, where we explain the reasons why objects move. But how fast objects move, that is closer. But to be more precise and like more generalized, kinematics answers the main question, which tells us how objects move in space and time, and solves quite a clear task. It predicts where, at which point of space, this considered body will be located at any given point of time. So that is the main task of kinematics. We just need to know, based on where body was and its main parameters, kinematic parameters, we need to predict where it will be and when. So that is what we are trying to do now with only the example of motion along a straight line. So this is one-dimensional motion along a straight line, and probably the easiest example we start from, but it will help us to introduce already quite many fundamental parameters which describe how body moves, and develop some analytical equation which will serve as a function of position on time. So it will be position along axis x as a function of time. So in order to come to these points, we definitely need to first introduce main parameters and then do some derivations. So let me change the screen. Okay. So if we now agreed that we will deal with single dimensional case, that will be motion along a straight line, there will be some axis, let's say x. It's quite straight line, as straight as I could draw it. And let's say we have some body located at initial position. Let's say it will be 0. So it's the origin of this axis x. So it can move in two directions, because it moves only along the straight line, either along the axis x or in the opposite direction. So let us consider first case when it moves along axis x. So it arrives after some time interval at new position, which is x1. And since we have motion only along straight line, we don't deal with vectors here. And the direction of motion will be defined by the sign of displacement and velocity. So if displacement and velocity are happening along axis, then they will be positive. So in this case, it will be x1 will be larger than 0. And if displacement is in the opposite direction than axis, let's say x2 will be smaller than 0, so will be negative. Also, so this case quite convenient because our body was located at the origin of the axis x. But if we consider a more general case, let's say initially body is located at some random position x1, then it moves along axis x and occupies another position x2, then the displacement will be just difference between x2 minus x1, and this will be larger than 0 because this motion was happening along axis x. So as I mentioned earlier, the main question which kinematics is trying to answer is how, where this body will be located at any given moment of time. So we want to have eventually some equation which will describe x as a function of time. So in order to come to this point, we need some parameters which will describe this motion. And let us go to another slide to have more space. Now we consider such plot. Will be x, position displacement along axis, and time. Keep in mind, it's not two-dimensional motion, it's not x and y. It's x as a function of time. And there will be some dependence like this. So means that initially, when we start motion from some point A, displacement will be positive, it will increase, and then it will be negative, so it will move in the opposite direction, and again becomes positive, so moves back and forth. So let us consider 2 points at time t1 and time t2. Also here we have x1 and x2. So this is interval delta t, which is defined as t2 minus t1. And this is interval delta x as x2 minus x1. So first parameter we will introduce, which is useful, but not sufficiently enough for deriving the final form of this equation, x is a function of t, but often used, is average velocity. So this is defined as x2 minus x1 divided by t2 minus t1, which is delta x divided by delta t, and that will be tangent alpha, and alpha is this angle of this triangle. So this is average velocity. It is useful parameter, but definitely it doesn't tell us how this body is moving at any given moment of time. It gives some average over relatively large interval, time interval. So in order to know exactly like full story about this body's motion, we need to introduce one more parameter, which is called instantaneous velocity. Means that this is the velocity at each moment of time. So how we get to this point? From this graphics would make sense to consider this interval shorter, like very short. So if we move this point T2 to point T1, it becomes shorter. Also, this interval with between position x1 and x2 also becomes shorter, and we can determine the tangent of this alpha within very narrow part of this curve plotted on our figure. And that is, from graphical point of view, actually introduction of derivative. So we consider V instantaneous, we just call it V, will be equal to limit of delta t approaches to 0 times delta x over delta t. So this is a mathematical form of defining derivative. So one short comment, here during this course of mechanics and like mostly mechanics, we will deal with such concepts as of calculus as derivatives, like limits, derivatives, differentials, integrals. You should be familiar with these concepts from the high school program. With it's only basics. Of course, you will have these courses of higher mathematics and calculus in your mathematics courses. However, at this point, it's required from you that you have basic understanding what these concepts are and know how to deal them on very simple fundamental level. So if by any cases you are not familiar with derivatives and integrals, please take some of your time and read just to know the basics. So this is definition of derivative, which is written as dx over dt. So from mathematical point of view, if we want to know velocity at some given moment of time, which is instantaneous velocity, we should take derivative of the function d, like x as a function of t over t, and take it at some specific moment of time. So that will give us the instantaneous velocity. Okay, so now we specified one of the key parameter, instantaneous velocity, and explained like the concept of this instantaneous velocity, how we can get it. there is still one more parameter which is left, without which we cannot be sure that we know this function. We have a chance to actually get this function. And that is acceleration. So acceleration, it's the speed of changing the velocity, how fast velocity is changing. It could be positive, could be negative, means when, for instance, some car is breaking down, like slows down, breaks down, the acceleration is positive or negative?
Negative.
Negative. Yeah, you're right, because we reduce the speed, and as a result of, and this reduction in speed is the result of negative acceleration. So it could be positive or negative, and obviously it will impact on the position of our body. So we need to know this acceleration because it has a big influence on the motion of the body. So as in analogy to the acceleration, to the velocity, we can introduce average acceleration, which is delta v over delta t. As I said, it's change of velocity over some time interval. But again, we need more. We need to know acceleration at each moment of time, means we need to deal with instantaneous acceleration. And this instantaneous acceleration also defines with this limit concept, delta t approaches to 0 of delta v over delta t. And this is not like anything else as first derivative of velocity over time. We know that velocity is given as the first derivative of position over time, like displacement. So in this case, we can write that acceleration is equal to the second derivative of this displacement over time, d square x dt squared. So these are the concepts of most important parameters which define the motion of any body. Quite general concept, but specifically in this case written for the case when we have motion along a straight line along axis x. So with this, we can proceed further and consider some example of such motion along a straight line and derive this equation x as a function of time, which is the main task of kinematics technically. So, of course, we will start with some simple case, and this will be motion along straight line with constant acceleration. Do you know any examples of such a motion along straight line with a constant acceleration?
Free fall.
Yeah, free falling, exactly. Thank you. So we have constant acceleration j, and it's motion along straight line. However, it's not the only possible case. You can also technically organize such motion if necessary. So we consider motion along axis x of some body with initial position x naught, initial speed, like velocity along axis x will be v naught, and this is larger than 0. And also we have constant acceleration. A is constant, and it is, let's assume it positive. So it increases velocity over time. So these are our given conditions. We know at t equal 0, our x is x naught. We know the initial velocity, and we know that acceleration is constant. Means it is the same at any given moment of time, which means that we automatically get instantaneous velocity, instantaneous acceleration, which is equal to this constant. So now let us write here how we define instantaneous velocity is delta x over, like dx over dt, and instantaneous acceleration is dv over dt. So let us consider this case first. We will go from what we know and step by step derive the rest of the parts of this equation. So we can rearrange this equation a bit. It will be dv equals to a times dt. So now we can integrate left and right side of this equation in order to get expression for instantaneous velocity. So we integrate left and right side. So we get from the integral in the left, it is just v. It's equal here a. We know that a is constant, so doesn't depend on time. We take it out from the integral sign, will be just integral of dt. And eventually we get a times t. So looks like we already got the equation which describes instantaneous velocity. However, it's not full picture yet, because when we have not defined integral, we have some constant, and let's call it C1. So with this constant C1, we need to define this constant in order to have the final equation. And constant is defined from boundary conditions. And in this case, this for velocity, it will be initial velocity v naught. So here, this constant C1 is equal to v naught. And eventually, we get expression for instantaneous velocity as a function of time will be equal to v naught constant, like initial velocity, plus a constant times t. So this is first important step on the way to derivation of this x as a function of t. Now we know velocity as a function of time, and let us check now this equation, which defines the definition of instantaneous velocity. Again, rearrange it and can write the following. It will be dx equals v times dt. Again, our goal is to know how x depends on t. So we integrate now from left and right. and get the following. Here will be just x. And here, instead of v, we should substitute its expression as a function of t. So here we will have in parentheses v naught plus a times t times dt. We know from rules of integration that the integral of the sum will be equal to the sum of integrals. So we can open this parenthesis and split this integral in two. So the first one will be, we have product v naught times dt. V naught is a constant, so we can take it out from the sign of integral. V naught times integral over dt plus, and here we have at times dt. A is the constant, we take it out from the sign of integral. And here we have t times dt. So these two integrals will be equal to v naught times t plus a times t squared divided by 2. So this is solution of this integral, and it's one of the standard integrals which are in the common tables of integrals. I'm sure you have seen those. Would recommend you maybe to print such table of integrals and maybe table of derivatives, just to have it next to your copybook in case you need to look it up, so you don't you know where it is and don't so it doesn't take much of your time and it doesn't disturb. Will be quite convenient to have it close to you. So again, it's not the full answer because we deal with not defined integrals. We will get some constant C2, which should be defined from boundary conditions. And again, this, since we are already operating with x, this is the initial coordinate of our body, x naught. So now we can rewrite it as x as a function of t time is equal to x naught initial position plus v naught initial velocity times t and plus a t squared divided by 2. This is the main equation we were looking for, and we actually, for this specific case of the motion along straight line with a constant acceleration, we have answered the main question of kinematics, because now with given initial position, initial velocity, and acceleration, we derive equation which gives us capability of calculating position of this body at any point of time t when we need it. So the main answer, like question of kinematics, is kind of answered in the form of this equation. So one comment, by the way, if you remember that during our second lecture, we were discussing dimensional analysis, and there was some example with position proportional to a acceleration times time. So with the help of dimensional analysis, we got the estimation that it is proportional to a times t squared. So you see that it was quite close to the reality, we get in the numerator a times t squared as a precise analytical solution of this case with this 1/2 coefficient. So you can compare the two absolutely different approaches to come to this equation, which provides a relationship between position of the body with some constant acceleration and time.
Mr. Brus, can I ask a question?
Yes, sure.
Well, not a question. Shouldn't that be plus minus before the at squared over 2?
That would be true, but we can also write plus minus next to v naught times t, because that is that depends either our initial velocity and acceleration were positive or negative. So if we come back to our previous slide, here we clearly define that in our example, v naught is larger than 0 and acceleration is also larger than 0. That's why along this derivation, we stick to these conditions and end up with this equation. But you're right, if our conditions would be different, means v naught and a are negative, we would get different signs.
Okay, thank you.
Thank you. Yeah, so another comment when you, and for sure you will at some point, try to derive some equations which describe certain physical, chemical, biological processes. It is definitely important to understand that you will do it in the framework of some model and some initial conditions. And that is very important to specify it correctly and be aware of them, because the analytical equation which you derive eventually to describe certain process will be valid only within those frames of the model and initial, like accepted model and initial conditions, which you started to deal with at the early beginning. So if those are changing, definitely your solution will not be applicable to the real problem. So this is very important to remember with what you start, which limitations are there and which conditions, and then your solution should be applied only in those cases when these conditions are valid. Okay, so I guess we have still some time. If there are no other questions, we can maybe proceed a little bit further with considering the replacement of time from these equations and expressing velocity as a function of position. That is kind of specific case when which could be useful in solving problems where time is not specified, but there are some given initial position and velocity, and also final position velocity. Final position is given, but final velocity, for instance, is unknown. And with known acceleration, known initial and final position, you can get the final velocity. So let us start with this one. Let's see if we can finish it. Let us add to this equation, which we derived here, the previous one, which we derived earlier for velocity. it was V is equal to V naught plus A times T. So we have this system of two equations. And now we can do some manipulations with this. Let us express, maybe also can delete this. Let us express time from a second equation. So it will be time is equal to V minus V naught divided by A, by acceleration. And now we can substitute this expression of time in equation 1, and automatically we will get rid of time because we will already express this in terms of instantaneous velocity, initial velocity, and acceleration. Let us do it here. It will be x as a function of all other terms besides time. So it will be x naught plus V naught times V minus V naught divided by A, and plus A over 2 times T squared. So it will be V minus V naught divided by A squared. Okay, so now we need to open this parenthesis to see what we actually get. And also can rearrange also a bit the left side of the equation. So let us write x minus x naught. And here we have in let's take a look at the first equation, like here. It will be here, we have A in numerator and A squared in denominator. So if we get rid of this, then we just can write A here in denominator. It will be 1 over 2 times A multiply V minus V naught squared. That means that we can multiply the left side with 2A, and we will get 2V naught times V minus V naught plus just this parenthesis, which will be V minus V naught squared. Okay, just check if we didn't miss something. Looks like not. So now let us finally open this parenthesis in the right side of the equation. So it will be 2ax minus x naught equal to 2v naught times v minus 2v naught square plus, now we have this v minus v naught square, which will be v square minus 2 times v naught plus v naught square. Okay, so what do we see here? This term and this term we cancel out. Then we have here minus 2v0 square and here plus v0 square. So this and this we can also cancel out. And eventually we get the following. It will be equal to v square minus
V0 square.
v0 square. Yes. Okay. So now we can express v square from this equation. It will be v square is equal to v0 square plus 2a x minus x0. So this is another form of this kinematic equation, which gives us the relationship between instantaneous velocity, v, initial velocity, this constant acceleration, and is defined by initial position and final, like not final, but current position in a given moment of time. So that could be a useful equation for solving certain problems when time is not involved in the condition. And quite common practice to express time with some other parameters, substitute them in other equation in order to get relationship. For instance, we will consider some equation which describe trajectory of body which is moving at the angle to horizon. Then we can apply this approach in order to get the equation which describes the trajectory of the motion, because there we will get y as a function of x instead of dealing with two equations, y as a function of t and x as a function of t. Okay, I believe we are running out of time, and this is pretty much everything what I wanted to tell you. If you have any questions, you are welcome to ask. If you have questions a bit later, you can we can discuss them during our next meeting on Wednesday. There we will most likely already move to the motion into dimension space. Also, we will need to introduce the concepts. They are similar to these parameters like velocity and acceleration instantaneous. They are similar to those which we define in the motion along straight line, but there of course will be certain features which takes into account motion into dimensional space. So obviously we will deal with vectors, not just with quantity, some numbers, and where sign defines the direction of motion because of such limited options to move only along straight line, as we discussed during this lecture. Yes, sure, this will be, the video will be available for everyone to access anytime which is convenient for you. So we will.
Sir.
Mm-hmm.
In the long kappa exercise, we have like the questions: what is the fractional standard deviation of any given unit? So what is the fractional standard deviation? Is it the fractional uncertainty?
It's, well, first of all, I guess that's a bit repeating the previous year. So we figure out that there is no decent information on deviations in the textbook. So we were considering not providing these problems for homeworks. So you can find in this videos from the previous year, which there are links from which are mentioned in the manual of the course. So there is one of my lecture where probably half of the lecture are given explanation of these deviations, because students were asking for some additional introduction to deviations. I believe you can find all information there, so we don't really need this and don't spend time on these things during this year. So it will be definitely better, and of course this all of them will not be counted for your final grade, but I believe they are not supposed to be there, so we'll definitely mention about this issue. Because in the textbook, we just don't have proper description of these deviations.
So it means that in our midterm or final exams, we will not have that definition, the fractional standard deviation.
No. In final and midterms, you will not have problems with any calculations of standard deviations. It's actually not physics, it's just statistics. So of course, it's kind of important part, but it's not the way how you can evaluate your knowledge of physics by asking you to show how you calculate standard deviations.
Okay, thank you.
Mm-hmm. You're welcome. Okay, guys, thank you very much for attention. Yeah, it was nice to see you, and hope to see you on Wednesday. Have a good day and goodbye. Take care. Bye-bye.
Goodbye.
Thank you. Bye.
Thank you. Goodbye.
Thank you. Goodbye.
Goodbye.
Bye-bye.